Hello everybody, and welcome to your first instructional video for Math 1314 College Algebra. Just some things I want to share with you before we jump in and get started with the content. This course is handout heavy, so if you happen to need copies, please email me and we'll work out some arrangements to get you copies of the handouts for this semester. Another thing to keep in mind is that some would say that short videos are the best, and they're absolutely right. However, for this course, if I were to create short videos for each typical night of instruction that we would have, I would be creating 6 to probably 8 short 10-minute videos. So as opposed to doing that, I think the suggestion might be to do this. I'm going to try and create 2 longer videos. However, you're going to need some brain breaks. So when we get to a natural point where in the content where it kind of transitions to another topic, you might want to just stop the video, go take a break, come back, and then be refreshed a bit to persevere and continue with the next topic. Something else mentioned too on the ICR is that a scientific calculator is going to be needed. Of course, you can use a graphing calculator. I would never know that until it comes to test time. And when it comes to test time, I would notice with the video that you're using a graphing calculator. So here's a calculator, a scientific calculator that I have that's a good one for this course. It's a TI 30X2S. I think you can get these for about $10 at Walmart or Walgreens, and it's a pretty good little calculator for this course. So I'll be using this from time to time. Okay, and again, if you have any questions about calculators, please just feel free to email me. All right, the first thing that we're going to be looking at is a review of some algebra topics. This first section, this is the pre-chapter. This is not chapter 1. This is in your ebook or your loose leaf book or your hardback book, whatever you decided to purchase. This is section P-1, Algebraic Expressions. So this is a review of some of the content that's necessary for success in college algebra. So these first 9 questions are more term-based. They want to remind us these questions about certain terms. As a matter of fact, these first 9 questions appear on homework 2. So when you get to homework 2, you'll probably want to pull these out so that you can reference the answers that we get here. All right, in P-1 or P.1, Algebraic Expressions, we want to know that this set of numbers, as suggested by 1, 2, 3, 4, and 5, this set of numbers is called the set of natural numbers. In question number 2, notice that this set of numbers now have everything that was up here, but now include a 0. When we include the 0, this is now called the set of whole numbers. Okay, question 3, notice that we have the whole numbers, but we also have some negative numbers too. Okay, this is called the set of integers. Question 4. The set of numbers in the form a divided by b, a fraction, where a and b are integers and b cannot equal 0. We just don't divide by 0. It's a bad thing in math. Okay, this is called the set of rational numbers. Okay, so these are fractions, but more specifically rational numbers. Here's some examples. Notice that 7 and 9 are both integers. Perhaps we have -2 divided by 5. We have 2 integers. That satisfies a rational number. It could be that the 5 is negative. And also, as a reminder, the placement of this negative sign could be out in front of the total fraction. So all 3 of these right here, rational numbers, represent the same value. Another rational number might be 16 divided by 100, and I have ... Right. These numbers will repeat or they will end. If you were to put these numbers into a calculator, these rational numbers into a calculator, if you were to do 7 divided by 9 on the calculator, let's see if we can see what that looks like. Oh, well, 7 just popped up. 7 divided by 9. That decimal approximation keeps repeating. Now, that 8 that's there, the display can only house so many digits. So they went ahead and rounded up, but if this calculator could handle an infinite number of digits, then I would just have 7s all the way across. It's just what the capabilities of this calculator. So notice that this rational number, 7 divided by 9, it actually repeats. Okay, let's try another rational number, like 2 divided by 5. 2 divided by 5's decimal approximation is 0.4. 0.4 ends. Okay, that decimal approximation ends. So a rational number represents a number that is repeating or ending. So let's go to question 5. What about the set of numbers whose decimal approximations are neither terminating nor repeating? Well, that's a different set of numbers, and those are the irrational numbers. So that term kind of makes sense. They're irrational. They don't behave well. So what are some examples? Well, you may remember pi. Okay, pi is 3.1415, and it goes on forever. It never repeats in its decimals, and it never ends. Okay, if you look at the square root of 3, the square root of 3, if computed on a calculator, never repeats. There's no repeating pattern, and it doesn't end, even though the calculator cuts it off because we have a limited number of digits that we can display. Okay, let's see how we can compute square root of 3 and see what its decimal representation looks like. So we're looking for the square root key. So it's actually right here, and then above this caret key, this power key, we see the square root symbol, and it's in blue. So we have to hit second square root. Oh, excuse me, that's a little different one. That's for a different root. Let me back up. It's the key above x squared. So second x squared. Okay, and it opens up a parenthesis for us in case we have some more things to add besides just 3. So I'll enter 3, I'll close the parentheses, I'll hit enter. And if you just kind of observe this decimal representation, I don't see any repeating pattern. And just because the calculator cuts it off doesn't mean that it does end. This pattern suggests that that number continues without ending and never repeats. That's an irrational number. Yeah, another irrational number would be something like negative square root of 7. Or maybe 3 pi divided by 2. 3 pi divided by 2 almost appears to be rational, but what happens is you're working with an irrational number in this fraction situation, so it forces it to be irrational. Every real number is either a rational number or an irrational number. So any real number has to be one of the two. Just like humans. Humans are either male or female. 7, the commutative property states that if you add two numbers, no matter what order you add them in, you should get the same answer. So if you take 7 and add it to 3, you're going to get 10. Well, what if you added 3 plus 7? You're still going to get 10. So this is the addition property, the addition commutative property. Okay. And likewise, if you multiply A times B, okay, then that product has to equal B times A. So 2 times 5 is 10, and 5 times 2 is 10. The associative properties state that when you group numbers to add, if you add two numbers together first and add it to a third number, that would be the same as if you added these two last numbers together, took that sum and added it to the first number. For multiplying, the associative property is similar. If I multiplied two numbers A and B, whatever they are, together first and took that answer, that product, and multiplied it by another number, I would get the same answer as if I were to multiply these second and third numbers together and then take that answer and multiply it by the first number that I have. All right, the distributive property. It states that when you take a number A and next to a parenthesis, this implies multiplication, that when I multiply A times the sum of two numbers, that the answer is going to be found if you were to multiply A times B, and then plus, I have a plus here, if this has been a subtraction, this would be minus, the product of A times C. So what this says is I can add these two numbers together first because they're in parentheses, and that's order of operation to do that first. If I add these two together, get an answer, multiply it by A, that would produce the same thing as if I were to multiply A times B and A times C and then add that together. So like I said, on homework 2, the first 9 questions come directly from these questions right here on these notes. So this might be a good time to stop, go take a brain break, and then come back because we're transitioning to another topic. All right, the next thing we want to remind ourselves before we start our work in college algebra is we want to remind ourselves about the order of operations to evaluate these expressions for the given number. If you just look at these and by inspection and you eyeball this, you probably already know what you need to do. This is just telling us to insert 7 for every x we see in this expression, do the math and get an answer, and be done. Let's remind ourselves about the order of operations. So we're going to use that acronym PEMDAS. So P stands for parentheses, but mainly it stands for a grouping symbol. So parentheses are a grouping symbol. When you see that, you do that first. Now, a grouping symbol could be a set of parentheses. This is a comma, okay? Or it could be a set of brackets. It's just another set of grouping symbols. Maybe we're asked to find the absolute value of something. That would be the 2 bars with an expression in between. Okay, or that's another comma. A grouping symbol can even be a square root symbol. So these are grouping symbols. And we do those first when we encounter a problem that we're trying to evaluate. Okay, E stands for exponents. If you see an exponent in a problem, you would want to do that after you've done any grouping. M stands for multiplication. And D stands for divide. But we have to remember that if divide comes first, if you're looking at a problem from left to right, we would do the division before we do the multiplication. So we don't always do multiply before divide. It just depends upon what comes first as we view the expression from left to right. So left to right. So A stands for add. We're going to do that last. And S stands for subtract. And just like multiplying and dividing, we look at these and perform the computations from left to right. So if subtraction comes in a problem before addition, we would compute that subtraction piece first, and then we do addition last. Okay, so let's come over here and evaluate the expression for the given value. So it says evaluate x squared minus 6x plus 3 for x equals 7. So first thing I'm going to do is I'm going to substitute wherever I see an x, I'm going to substitute in 7. So keep the square. Now this is implied multiplication. So however you want to handle this, you can do a multiplication dot. You could put 7 in parentheses because that implies multiplication. And then plus 3. Now if you want to do this mentally, that's fine. It's not too cumbersome. Or you can do it on the calculator. So doing this mentally, I get 49 because I'm going to do a power first. That's an exponent. And then if I look to the right here, I see a minus sign, but I do notice multiplication, so that's minus 42. I'm going to keep the plus, and I'm going to keep 3. I'm going to come up here. Now with my new expression right here, I see a subtraction and an addition. So I'm going to do the subtraction first because it comes first when I work left to right. So 49 minus 42 is 7, and then I still have the plus 3. So the final answer, and I'm working down, is 10. So again, you could put that all in your calculator if you wanted to. Leave that lid. So 7 raised to second power minus 6 times 7, and then the plus 3. So I would just encourage you to check it with the calculator. You're able to use a scientific calculator, so let's not leave anything to chance. Okay. Same thing with number 11. Replace every x with 9. So 4 plus 5. Parenthesis, x becomes 9 minus 7, and then we take that to the third power. So if you're going to follow the order of operations, I see a grouping symbol here first. So I'm going to perform those computations first. Keep the 4, keep the plus, keep the 5. This is implied multiplication. This would become 2, but I still have the power. Well, checking our list here, what comes next? The power or the exponent. So I keep the 4, I keep the plus. I keep the 5, and I know this is multiplication. I could either use the multiplication dot, or I could do another set of parentheses where I'm going to perform 2 cubed. 2 to the third power is 8, so I'd put 8 in here. Scanning now the result here, I see multiplication. Multiplication comes before addition, so I've got 4 plus 5 times 8 is 40, and the final answer is going to be 44. Again, why bother with all that mentally if you're going to have a calculator? It just kind of be careful though when you put it into the calculator. So 4 plus 5, you don't need a times. 9 minus 7, close your parentheses. Your caret key is here, raised to the third. We should get 44. All right, I'm going to leave 12 for you to do. On Blackboard, you'll see an attached key with all the worked out solutions for every problem. So sometimes on the videos, I won't be able to get to every single problem, just kind of leaving it for you for practice. And so, but I will have the attached worked out solutions, the keys for all the notes. Okay, this might be a good time for a brain break as well. We're at almost 16 minutes. All right, take a moment and read through problem number 13. Stop the video, read through it, process the question. Kind of imagine what you think you would do. I think that's a good learning strategy. Read a problem, guess what you think would think that you would do, and then see if it's confirmed when we do actually solve the problem. So a football was kicked vertically upward from a height off the ground of 4 feet with an initial speed of 60 feet per second. This particular formula, h, height, as a function of t, or time, describes the ball's height above the ground. H in feet, so h is given as units with feet, and t is seconds after it was kicked. What was the ball's height? So we're finding h when 2 seconds has passed, when time is 2 seconds. So intuitively, I'm hoping you're thinking, oh, I'm going to plug in 2 for all the t values and compute the height. I'm going to add a little bit to the formula. I'm just going to transpose it down here. Notice what I added. I added a parenthesis of t and then an end parenthesis. This does not mean multiplication. In context of this problem, I could be a little bit better with my notation. Instead of just using h, I could say that h is a function of time. This just gives us a little more information that the h, the height of the ball, is dependent upon the time that the ball's in the air. So again, this is not multiplication. It's just a different label for h. Just like I'm Kim, I'm Mom, I could be Grandma, I could be Mrs. Fudge. You know, there's different representations for me. Well, there's different representations for h. And just because I have h of t, that is the same thing. It means the same thing as just h right here. It's just a little more descriptive. It actually just tells us that, hey, hold up, look, there's a t inside this equation. So what I'm going to do is I'm going to insert 2 for every t here, which I'm also going to insert 2 here for that t. So this is going to be read to us as the height at time 2 is equal to 4 plus 60 times 2. Now again, you can use a multiplication dot or you can use parentheses for implied multiplication, minus 16 times 2 squared. You'll go to your calculator, you'll compute that value, or if you want to do it without a calculator using the correct order of operations, the answer is going to be 60. And it would be best if you put a unit on the answer. Well, what is 60? 60 is the feet at 2 seconds of that football. So hopefully intuitively you kind of knew that that was going to be what happens, and that does exactly, that's exactly what does happen. All right, let's transition here now. 14 and 15. Write each algebraic expression without parentheses. Well, when I look at this and observe what it's asking me to do, it's saying take the opposite of this negative 14x. Well, when you subtract a negative number, that turns it to positive, so actually those two negatives undo each other and we're left with 14x. With 15, notice that we have actually 3 terms. Terms are what you add and subtract, terms are what you add or subtract to each other. So 2x is a term, negative 3y is a term, and negative 6 is a term. I'm taking the subtractions as a negative when I read it back. Notice that up here, this was just one term. So what happens when you have the opposite of all three of these terms? Well, one at a time, you change their signs. So what we're doing is we're distributing that negative inside. You can also think of this negative with the understood one here of being the distributive property, where you multiply negative 1 into each of these three terms. So the answer is negative 2x plus 3y and then plus 6. Depending upon your level of comfort with math, I might suggest that when you're looking at the notes, try and do as much of it as you can before you actually watch the videos or you look at the worked out solutions. It's best for you to attempt and take those risks, and try and figure out what the answer is. And who cares if you're wrong? I mean, nobody's going to care. You're just guessing. It's just better for the learning. I think it cements it a little bit better. Okay. Having said that, if I go through a couple of examples and you're struggling, then I might suggest that on the Start Here button, I provided some resources, some additional resources for you to seek out and to help you and assist you with any difficult concepts or topics. For example, let's say we're covering exponents, okay? And you're going, oh my gosh, that just wasn't enough examples. I need to see more. Well, go to Patrick JMT or just Google it and look for properties of exponents, and you'll get all kinds of videos that you can watch. Okay, so why don't you take a few moments and see how many of these questions down here that you can answer, and these are based on properties of exponents. Okay, 16 says, if I have a base, this is an exponential expression, if I have a base of x to the 11th power and I'm multiplying it by another base of x to the exponent of 5, properties of exponents say keep the same base, whatever that is, and we add the exponent. So 11 plus 5, so that would be the same thing as x to the 16th. So that's your answer. Kind of the math behind this, x to the 11th means I have x times x times x times x, and that goes on dot, dot, dot until you get 11 x's. This means multiply, repeated multiplication, multiply 11 x's together. Well, then we approach this multiplication symbol right here, and then we're going to multiply that by x to the 5th. Well, x to the 5th can be represented by 5 x's being multiplied together. Well, when I multiply all these x's together, count them up, I'm going to get x to the 16th. All right, property of exponents here. If I have a fraction, notice that both of my exponential expressions right here, my power expressions, have the same base. Now, this works only if I have the same base. If this is b to the 5th, I couldn't do what I'm about to do here. Okay, this property works here because I have the same bases of x. Had this base been a y, I couldn't add the exponents. So when we divide, we actually subtract the exponents. So 14 minus 5 is a to the 9th. And that's the answer. The math behind that, if you want to kind of see it and view it, is look at the numerator. If I expanded that exponential expression there, I would be multiplying 14 a's together, dot, 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 and I eventually get to the 14th a. In the denominator, I'm multiplying 5 a's together. Well, what we can do is, if we have factors, we can reduce. So I could divide out that a and that a. I could divide out that a and that a, that one and that one, that one and that one. And if I had one more a here to divide with this a down here, I would have nothing but a bunch of ones in the denominator, but I'd still have 9 remaining a's in the numerator. So you can think of that as a to the 9th over 1. But this isn't necessary. It's not wrong to put this fraction over 1. It's just simply a to the 9. Okay, number 18. Notice how 18 and 16 are similar. You might think the answer is also x to the 16th, but it's not. This is a power to a power. What this means right here is that I have this parenthesis, x to the 11th, taken and multiplied together 5 times. So if I have this expression right here, Now I'm back to a problem like number 16, and what I'm going to do is I'd add all these 11s together, and I'm going to get x to the 55th power. Well, instead of doing all this work, you can, but instead of doing it, how can I quickly go from the problem to the answer? When you have this situation, a power to a power, you can just multiply the two exponents. Up here we added, because we had two of similar bases. Here we only have one base, so we multiply the exponents. All right, 19. Okay, so again, like 18, this power to this expression right here means that we have two of these parentheses being multiplied together. I'm going to expand this expression. Okay, now I can kind of ignore the parentheses. Let me tackle the numbers first. 6 times 6 is 36. Okay, now let's look at the variable factors. X to the 4th times x to the 4th is x to the 8th. Can you see a way without having to go through all this work to go from the problem to the answer? Just be careful. A common mistake is students will forget to square the number and forget to get 36. They'll just get 6. They will mostly remember to multiply the exponents and get x to the 8th though. So be careful. And 20. What does 5 to the 0 mean? Take a guess. Is it 5? Is it 0? No. Any number to the 0 power is 1. That might be a good thing to memorize. Maybe something to write down. Anything to the 0 power is equal to 1. Okay, so what's the math on that? Because that's often asked. Okay, so let me give you an example. What if I had 5 to the 3rd divided by 5 to the 3rd? And we're thinking about what our work was back up here in this property. Well, same base, subtract the exponents. Okay, well, when I subtract 3 and 3, I'm going to get 0. Okay, well, how does that equal 1? Well, let's think about that for a minute. This number, 5 to the 3rd, is going to be the same number as this number down here. So in a fraction, when you divide a number by itself, you're always going to get 1. So 0 just means that when you're subtracting the exponents, you get 0. And so that must mean the two numbers are equivalent, and a number divided by itself should always be 1. Okay, 21 is kind of weird. So how do we handle negative exponents? I think the best thing here is for me just to show you the answer and then do a couple of quick examples over here off to the side. Okay, x to the negative 3. When you see a negative exponent, it's not bad to have a negative exponent. It's a choice that maybe someone would say to you, rewrite that negative exponent as a positive exponent. Well, what's the math that allows us to change that negative 3 to a positive 3? Well, in this case, I would build a fraction bar. I would observe the factor that's in front of x. Well, there's not one, so the understood factor is 1. So 1's exponent is not negative. 1's exponent is actually just 1. So I would leave a 1 on top. Okay, and I would actually move x to the denominator. And when I do that, I'm going to adjust that negative and make it a positive exponent. So let's say now we have a different problem. Let's say we had 2x to the negative 4. What do you think that is? Rewritten as with a positive exponent. Well, 2's exponent, this factor 2, has a positive exponent of 1. So I'm going to create a fraction bar. The 2's good to stay in the numerator, but we're going to place x in the denominator, and when we do that, we're going to adjust and make that exponent positive. Kind of a quick way to make any negative exponents positive if we care to have them positive. Now, I don't care if they're negative, but in case you're asked to give a different form with a positive exponent, that would be your approach. Let's look at another example. Okay, what about 6x to the negative 2, and I'm going to throw in a y variable, okay, another factor, but it's going to have a positive exponent. Okay, so I love that problem. It's fine. But what if someone turned around and said, can you rewrite that? Can you rewrite that so it doesn't have negative exponents? I'd be like, sure. So how would I do that? Well, when I see a negative exponent, I know I'm going to adjust. I'm going to move x squared to the denominator. 6 stays in the numerator. Y to the 4th stays in the numerator. So the only thing that's going to be in the denominator is the base of x, and adjusting to make a positive exponent. No, it's a little bit weird. It's just the movement from numerator to denominator. Okay, and maybe one other weird kind of abstract problem. Hopefully we can still see this here. Yeah. Okay, what if we had a problem that looks something like this? What if we had 5 over x to the negative 6? That's kind of weird. Okay, so what do you think? Well, negative exponent, let's make it positive. What do I do with it? I've already got a fraction here. Well, let's move it to the numerator. So 5's in the numerator, it's good to go. If I adjust and move x to the numerator, I adjust the exponent and make it positive. That might be something that you'd want to Google and look more at, negative exponents and how to rewrite. It doesn't come up a lot, very little, but just wanted to put it out there. Okay, let's look at 22. Okay, we're asked to simplify this expression. So how we handle this is, let's look at the factors that are just numbers. Well, 35 divided by negative 7 is a nice number. I can simplify that to negative 5. Now let's handle these next factors right here, because we can reduce factors. So same base. So what do I know about fractions? I subtract the exponents. So I'm going to get a with the 7 exponent. Move on to the next factors in the problem. They're both b's. So again, a fraction. So let's subtract the exponent. So 6 minus 3 is 3. So that would be a simplification of that fraction. Okay, I'm going to stop here. We're about a little bit over 30 minutes, and so I'll create another video that completes this packet.